Hello everyone, welcome back to the continuation of discussion of analysis of bars using FEA technique or FEM methods. We have started the discussion or analysis of bar elements, one-dimensional bar elements using FEM technique. In the previous problems, we have used elimination approach to solve the problem. There is one more approach or one more method, that is penalty approach or penalty approach to solve the same problems, one-dimensional bar elements. We will see that kind of problem in today's session. So one problem statement I will read here. An axial load of P equal to 200 kN is applied to the bar element as shown in the figure. Calculate first one nodal displacements, second stresses in each element, third reactions at a support. Fine? But he particularly mentioned as use penalty approach here. So we have to go for penalty approach. If he didn't mention, either you can solve by using elimination approach or by penalty approach. But if they particularly mention one particular method, we have to solve by that particular method only. Fine? So diagram is given that I have drawn on the board already. There are stepped bar which is fixed at both the ends. The point where there is a change in cross section, there is a load P is acting. That value is given as 200 kN. And the first element that is made up of aluminum, other element that is made up of steel. And cross section area is also given for aluminum 2400 mm square, for steel it is 600 mm square. And he has shown arrow mark, and it is x equal to in this right side, towards right side. We have to consider this direction as positive direction. Any forces that are acting towards right side, they are positive. If the force is acting towards left side, which is opposite to the given direction, then you have to take as negative value. Fine. And length of the elements is also given. For aluminum it is 300 mm. For steel it is 400 mm. This is what and one more parameter that is required. There is material property Young's modulus E equal to. For aluminum it is 70 into 10 to the power of 3 Newton per millimeter square. Whereas for steel it is 200 into 10 to the power of 3 Newton per millimeter square or megapascal. Now, say in this method also, all the first four steps that remain same. Which are those? First step is that is discretization or drawing the FEM model. Second step, finding the elemental stiffness matrix for each element. Third step, assembling or adding all stiffness matrix and getting the global stiffness matrix. That is global stiffness matrix. That is step number 3. That also remains same. Step number 4, global displacement vector. That also remains same. Before going to step number 5, there is small change in this penalty approach method compared to the elimination. So first, I will explain all 4 steps in short, because you already know that how to write these all 4 steps we have seen already in the previous problems. Fine. First step is drawing the FEA model or discretization. First, I will draw the line diagram. Here I have to represent nodes, elements, and given boundary conditions. Say I have drawn a line diagram of similar length. Now, where I have to take the nodes? We all know that in extreme ends, if there is change in cross section or if the particular load is acting at a particular point, in that region we have to mention the nodes. So at this end I have taken one node, at this end one more node. Here there is change in cross section, at the same region one load is acting. So here I have taken one more node. Total there are 3 nodes. Now we have to give node numbering. So I will take this node as 1, this node as 2, this is third node. 1, 1, 2, 3. And element number between node 1 and node 2 is element number 1. Alright, 1 here and you have to encircle. For this is between 2 and 3, this is element number 2. Always element number has to be encircled. At node 1 displacement is q1, at node 2 displacement is q2, at node 3 displacement is q3, and in element number 1 stress is sigma 1, in element number 2 stress is sigma 2. L1, the length of element number 1 is given 300, L2 is 400 millimeters. This is first step. Now, and we can show the boundary condition also. Node 1 is fixed. It means what is that? What is the meaning? If there is fixed means displacement at node 1 q1 equal to 0. Node 3 also fixed here. Here, fixed means there will be no displacement. Displacement at node 3 q3 also 0. Next, step number 2. That is finding stiffness matrix for elements. Elemental stiffness matrix. General formula is K equal to K is nothing but stiffness matrix. Always it should be written in square bracket. K equal to AE upon L multiplied by the matrix. The elements in the matrix are 1 minus 1 minus 1 1. This is the general stiffness matrix for one-dimensional bar mill. Now you will be knowing cross-section area, Young's modulus, and length of element. Substitute them and find the value of K. Now K1, that is the elemental stiffness matrix for element number 1. K1 equal to cross-section area is given to you 2400 millimeters square, and Young's modulus 70 to 10 to the power of 3. Length is 300. Sorry, I will do 300 millimeter. So multiply this, you will get 0.56 into 10 to the power of 3. This entire thing 0.56 into 10 to the power of 6. So instead of multiplying that term to the entire matrix, what I will do, 10 to the power of 6 I will take outside as a common element. Remaining value 0.56 I will multiply inside. Or else you can take 10 to the power of 5 outside. What will be remaining? It will be 5.6 that you can multiply inside. That is of your choice. But one thing you have to take care is the whatever value you are taking outside here, the same value you have to take in the next stiffness matrix also. That will help us to find global stiffness matrix. Right? So multiply this. This will be 10 to the power of 6 into 0.56. 10 to the power of 6 I have taken outside. Remaining value I have written inside. See, 0.56 minus 0.56 minus 0.56 minus plus 0.56. 0.56. Now after this one, you have to give row numbers and column numbers. They are nothing but node numbers. For element number 1, K1 means it's for element number 1. For element number 1, what are the nodes? Node 1, node 2. Initial node is 1, final node is 2. Right? So 1, 2 I have written here. 1, 2. This is column number 1, column number 2. This is row number 1, this is row number 2. Similarly, for element number 2. Again, this is the same general formula. Here it will be A2, E2, L2. Substitute those values. There we are getting this entire term, 0.3 into 10 to the power of 6. We know that the same value we have to make outside, so 10 to the power of 6 I have taken outside, 0.3 I multiplied inside the matrix. We are getting this as the matrix here. Again, we have to give the numbers 5, 2 and 3. Row 2, row 3. Look at the diagram. For element number 2, nodes are 2 and 3. Initial node is 2, final node is 3. So that is the reason 2, 3. 2, 3. This is the column 2, column 3, row 2, row 3. There are 2 elements, 2 stiffness matrix, that is K1 and K2 that we found. Third step is adding these two, that is assembling elemental stiffness matrix to get global stiffness matrix. Global means stiffness matrix for entire structure. Step number 3, global stiffness matrix. What I will do, 10 to the power of 6 that is common for both the stiffness matrix. I will write as it is. Here also I will take it outside. I will write a matrix and keep it blank. What are the terms you have to write inside? We will see it later. There is a particular method we have seen, we have followed in the previous sessions also how to get these elements inside the global stiffness matrix. We know that there are three nodes, 1, 2, 3. The matrix what you are getting, it is of 3 cross 3 set. So I will give the number set. 1, 2, 3, 1, 2, 3 column. There are 3 columns, 3 rows. Right? Then how to write this? See, in this place, first element is nothing but K11. This is K12, K113 like this. First suffix 1 is nothing but it is row. Second one value is column. Here 1, 2, row number 1. Second is column number like this. Fine. Here, row 1, column 1. Look at the elementary stiffness matrix. Row 1, column 1, the value in that region, in that case, value is 0.56. So, at the point, at the place, row 1, column 1, I will write 0.56. Similarly, row 1, column 2. Row 1, column 2, it is minus 0.6. Row 1, column 3 is not available in the both matrix, so that value becomes 0. Now, row 2, column 1. Row 2, column is 1, this is minus 0.56. Similarly, row 2, column 2. What is that? Row 2, column 2, it is 0.56. Similarly, here also we will get row 2, column 2. The two values we are getting, you have to add those two values and write it. 0.56, 0.3. That is 0.86. This is a very important step here. We are getting in the same region, two values we are getting added. Next, row 2, column 3. Row 2, column 3 is not available in here. Row 2, column 3 is minus 0.3. Next, row 3, column 1. Row 3, column 1 is not available in both the matrices, so I write it 0. Row 3, column 2. Row 3, column 2, that is minus 0.3. Next, row 3, column 3 is not available in this matrix. Come to the second element. Row 3, column 3, it is plus 0.3. See, this is the way to write down all the elements in global stiffness matrix. Fine. Next, step number 4. Step number 4, displacement vector. Nodal displacement vector means what are the nodes, what are the displacement at each node. So Q equal to displacement we are representing here Q, or in some books they will use the rotation as U. Whichever is convenient that you can follow. Q equal to Q1, Q2, Q3. This is the displacement vector. Right? Very next step is step number 5, that is global force vector. Okay? Compared to the previous method, elimination method is quite different. That's why I will keep it as it is. Now I will explain about how to find penalty term. Penalty term that I will represent by C. Because the method what we are using here is penalty approach. That's why we have to find penalty term C. How to find this one? C. C equal to maximum value of global stiffness matrix. Maximum value of Kij. K means these terms. I means row. J means column. Maximum value of this term, this matrix into 10 to the power of 4. You have to find maximum value in this global stiffness matrix and multiply by 10 to the power of 4. See here, which is the maximum value in this matrix now? That is 0.86 is the highest value. That is bigger value. It is in which region? It is row 2, column 2. K22. K22 is 0.86. For that, it's not only 0.56, outside there is 10 to the power of 6. So, maximum is 0.86 into 10 to the power of 6. Here, multiply by 10 to the power of 4. 10 to the power of 4. This is the penalty term C. In this way we have to find. This term we have to add to this global stiffness matrix. Where I have to add? Whether I have to add to all the elements or at a particular element. That we will discuss it. See here. This is the penalty term. We discuss about this. C equal to maximum value of Kij into 10 to the power of 4. We are getting this way. 0.86 into 10 to the power of 6. This is the highest value multiplied by 10 to the power of 4. And this above value of the C to K11 and K33. Where the K11? See, this is the reason. Row 1, column 1. This is K11. And we have to add to K33 also. Row 3, column 3. Here also we have to add this value, C value. Find particularly at K11 and K33. It means wherever the displacement is known for us. It means at a particular node, if the displacement is known for us, at that region we have to add this penalty term. Clear? How we will confirm here at node 1? See K11. Why K11 only? Because at node 1 displacement is known for us. How much it is? It is 0 because that node 1 it is fixed. You can look at the diagram. Node 1 is fixed. So we know that displacement Q1 equal to 0. That's why we have to add C term to the K11. And we have to add C value to K33 also. Why? Look at the diagram. At node 3, there also displacement is known for us. How much it is? It is also 0 here. Because Q3 equal to 0. Because node 3 is also fixed. So wherever displacement is known for us, at that particular node, we have to add the value of C term. It means it understood that displacement at node 1 is known for us. Here we have to add C term at K33. Here also we have to add C term. How much is C term now? We'll have C this much. While adding, we cannot add this entire term inside the matrix. So before adding here, 10 to the power of 6 already outside. First, you take 10 to the power of 6 outside, then remaining value you can add it to the matrix here. This is the one common mistake what we will do in a hurry. Entire thing we will try to add to the matrix. No. While adding, the common term whatever we have to take, that we have to take no. So 10 to the power of 6, that we have to take outside. Remaining value is how much? 0.86 into 10 to the power of 6. 10 to the power of 4. That is, I think that is 8600 we have to add inside the matrix. That is in this region and this region. Clear? How to find the penalty term and where we have to add in the global stiffness matrix. So, how much it is? This becomes 8600.56. This also 8600.3. Please note the difference. You are not supposed to write here only. In the next step, there you can add and add. I have added in the previous episode just to tell you where it comes, how it comes. Next. Because node 1 and 3 are fixed, and also you have one more sentence here. In this region, we know the displacement. Wherever displacement is known for us, there you have to add this. Also add CA1 to F1, CA3 to F3. We know value of C, the term C, but what about A? A1, A3 and all. It means A is nothing but known displacement. Known displacement. Suppose the given diagram is like this. Here one node is acting. P. So for this, we will draw the diagram. At this end, there is one node. Node is acting. Here one more node. And at this end, there is one more node. Suppose this distance gap is given to you, 0.1 millimeter. See, this is node 1, this is node 2, this is node 3. At node 1, displacement 1, it is 0. This is known for us because it is fixed here, q1 equal to 0. At node 2, we need to find the displacement. What is the displacement at node 3? This is also known for us. See, if you apply the node, this is going to expand up to this support. After that, it is going to stop here. What are the displacement? Node 3, how much is going to displace? There is maximum value is 0.1 millimeter. That is also known for us. So, this node displacement we will represent as A0. Here, at node 3, displacement is known for us. That I will call it as A3. Right? At node 1, there is no gap like this or no displacement. That's why that value is 0. A1 is 0 here. Clear? Have you understood what is the value of A here? A is nothing but one, you can call it as the gap between the structure and the support, or you can call it as node displacement. Right? What happens in this case? We will discuss in the next step. Step number 5. Now, step number 5, that is global force vector. So before coming to this, we have discussed about how to find the parameter C and how to add it to the global stiffness matrix and what is the value of A also. Here also, there is slight change in finding the force vector compared to the elimination approach. F equal to, earlier we used to write F1, F2, F3. Here, F1 plus CA1, F2 and F3 plus CA3. C is nothing but penalty term. A is the known displacement or gap between given structure and the support. Here, look at the diagram. At node 1, there is no gap. Hence, A1 value is 0. This value becomes 0. So, 0 into this C, this becomes 0. What is remaining? Only F1. F1. How much is F1? What is the force acting at node 1? There is no force acting at node 1. That's why F1 value I have written at 0. And at node 2, there is no support. We don't know the displacement, so we are not going to add any value of C and A here. So directly write down F2. At node 3, it is also displacement is known for us. How much it is? 0. That is fixed. That's why we have to add CA3 to F3 also. That is, F2 is how much? It is given in the problem statement. At node 2, 200 into 10 to the power of 3 is the load acting. That I have written here F2. And here F3, no force is acting. This is 0 plus C. We have a value that is 0.86 into 10 to the power of 6 into 10 to the power of 4 into A3. What is A3? Displacement at node 3, that is 0. There is no displacement. Gap between structure and support. There is also 0 here. 0. This is 0 into this term becomes 0 plus F3. There is no force is acting at node 3. That force is also 0. 0 plus 0 is also 0. Clear? This is a force vector. Quite different step compared to the elimination approach in the penalty approach. But 0, 200 into 10 to the power of 3, this is 0. Next step is step number 6, that is equilibrium equation. This remains same. Equilibrium equation. K into Q equal to F. KQ equal to F. K is nothing but global stiffness matrix. We have added a penalty term here. After adding penalty term, see this term change compared to the previous global stiffness matrix because of penalty approach. This is K, Q. We know that in the step number 4, Q is nothing but Q1, Q2, Q3. So Q is here, K is here, Q, F. There is force vector. Nothing but here. Then also we have 0, 200 into 10 to the power of 3, 0. I have written here. This is equilibrium equation. What is next step? Earlier, in the elimination approach, we used to eliminate particular number of rows and columns. Here, we are not going to do that because we are solving it by penalty approach. So, write down this matrix in the form of equations. 10 to the power of 6, into this one into this, like this. You write down 3 equations. Solve those 3 equations. You will come to know these unknowns: Q1, Q2, Q3. There is nothing but displacement at node 1, 2, 3. For solving this one, there are 3 equations. You can fill those values in the equation. In the calci, go to the equation mode. There you can enter all 3 equations. You will find Q1, Q2, Q3. Fine? Okay. Fine. Step number 6. That is equilibrium equation. K, Q equal to F. We got matrix. That matrix we have written in the form of equation. So 3 equations you will get that are written here. Solve these 3 equations. So in calculator you can solve it very easily. Go to the equation mode and enter these all the values. You will get 3 unknowns. This is Q1, Q2, Q3. Q1 we are getting is 1.5 into 10 to the power of -5 millimeters. Similarly Q2, Q3. See, one question arises here. Node 1 is fixed. It means displacement has to be 0. But we are getting as 1.5 into 10 to the power of -5. It is nothing but almost equal to 0. It is 0.0001. Almost equal to 0. Similarly at node 3 also. Node 3 also is fixed. Here also Q3 equal to 0 as we discussed. You can look at the value. It is 0.00008. It is almost equal to 0. Okay. For further calculation, you may use 0 or you can use the same value what you are getting. The answer, final answer should be correct. Same. Next, we have this is how to find the nodal displacement at each node. That is Q1, Q2, Q3. Next thing, he has asked to find stresses in each element. What is that? Stress in each element. So, equation to find the stress is sigma equal to E upon L minus 1 Qi and Qi plus 1. Qi is nothing but for element number 1, this becomes U1 L1. This will be given to you. What is the property? Length is also known. Minus 1 Qi. What I have write? Node number. What I have write? This is for element number 1, sigma 1. For element number 1, nodes are 1 and 2. So it becomes Q1, Q2. That I have written here. The values I have entered, and this becomes Q1, Q2. We have the value of Q1. Substitute this one. We have the value of Q2 here. Substitute here. Find the value of stress. Sigma 1 equal to, we are getting at 54.25. I will suggest you people to check what are the values I am getting here. Once again, cross check it. Okay. And sigma 2 equal to E2 upon L2. General equation is E upon L. This is for element number 2, E2, L2. And here, again, node numbers which I have to use. For element number 2, node numbers are 2 and 3. So Q2, Q3. You know the value of Q2, Q3. They are available here. Substitute here. And sigma 2, stress in element number 2 is minus 106.25 megapascal or Newton per millimeter square. Okay. And one more thing he has asked us to find, what is that? Reactions and a support. Reaction forces and a support. Step number 8, reaction and a support. For current approach, the equation what we are using, that is nothing but R equal to minus C into Qi minus of AI. R is reaction force. C, the penalty term what we have found in the previous step. Qi, the nodal displacement. For which node we are finding the reaction. For element number, for node number 1 you are finding, it becomes Q1. If you are finding reactions at 2 or 2 equal to, it becomes Q2. Minus of AI. What is A? This also we have discussed. What is the meaning of A? It is the distance or the gap value between structure and support. Here there is no gap, so this becomes 0. This value becomes 0. So what is remaining? Minus C. This is Q1. Minus C into Q1. You know the value of C. You know the value of Q1. That is displacement we found. Substitute that. You will get R1. Similarly, reactions at node 2. At node 2 there is no support. No need of finding the reactions at node 2. Leave it. Directly take node 3. at node 3 there is support, it is fixed. So I have to find reactions at the third node, R3 node, minus C. Write it. It is Q. Since we are finding the reactions at node 3, so displacement at node 3 is Q3. So write down that is Q3 minus of A3. AI means something, but it is A3. A3 is also 0 in this case. In this case it is 0 because there is no gap between support and structure at node 3. So this also becomes 0. So 0. Remaining is minus C into Q3. Minus C into Q3. This value also you know. This also you know. Substitute that. You are finding R3. R3 value you are getting at minus 69.75 10 to the power of 3 newtons. This is the force. That's why the unit is Newton. R2, you know that there is no support. That value is 0. So we found R1, R2, and R3. Clear? This is the penalty approach. First 4 steps that remain same. Remaining finding the force vector and finding the penalty term. That is quite different here, and I have explained in detail. And there is a change in finding the reaction supports also. The equation is quite different compared to the elimination approach. So this is the way how to solve the one-dimensional bar element using penalty approach. Hope you all have understood.